9:01, and for these things, it's very easy to be on time. Let's start on time. So, welcome everyone. Thank you for being here. We're gonna start with the class. Everything is going to be recorded. Anytime you want to make a comment, go ahead and make it. The plan is that, like I was saying, either Bruce or myself, we're going to be talking for about 20 minutes, and then we're going to have a 10-minute session, and we're going to have 6 of these 30-minute sessions. All right, so let's get into it. The schedule that we had, we already saw it, and feel free to jump in, to leave anytime you want to or come back. Everything is recorded, like I was saying, and we're going to post it on YouTube. We're going to start with an introduction without actually using the software. Then we're going to see some of the very basics of UTAPWeLS. Some of the experienced users have already seen this, although it has a twist because we have done a lot of improvements. I'd like to call them improvements regarding exactly that, the visualization. Then we're going to talk about simulations and physical properties inversion, what we usually refer to as MCMC, even though it's not always MCMC, Markov Chain Monte Carlo. Then we're going to do a compositional joint inversion, which is one of the modules that has been more recently developed, and I know a few companies are interested in this. Then we're going to have an NMR module that has been expanded in the past couple of years. It's very thorough. It's one of the most thorough modules that I've seen. And lastly, the fluid flow simulation, which is another staple of UTAPWeLS. All right. Now, most of you guys already know it, but for the truly new users, I'm going to remind you that we have 3 types of UTAPWeLS installers. UTAPWeLS is developed always in MATLAB. So we have a MATLAB-based installation, which means that you have MATLAB installed in your computer. We send you the files, and you can work with it. This one gives you the option of doing scripting, which is being able to write MATLAB code that is going to modify all your data in UTAPWeLS. You can access it. You can do everything you can do with MATLAB, you can do with your data, plus everything UTAPWeLS, the visualization, the inversion, all the algorithms that we already have. Then we have the standalone MCR. This is the standard version. This is the default version that most people use. MCR stands for MATLAB Compiler Runtime, which is MATLAB without full MATLAB installation. So it allows you to run everything MATLAB without actually using MATLAB. This is what you install when you install UTAPWeLS. And because you install MCR, once you have installed the standalone MCR, it's possible to install it again without actually installing the MCR, which has the benefit of not requiring admin rights. Lately, because computer, IT protocols have been changing a lot in the past 5 years or so, or in a long time, some companies don't even allow you to install this, which is a pity, but that's okay. Anytime you get the link to download UTAPWeLS, you get these 3 options. All right. Now that we've talked about that, let's talk about actual UTAPWeLS. So UTAPWeLS, as you already know, is the University of Texas at Austin Petrophysical and Well Log Simulator. That's what it stands for. And it's a software to construct an accurate Earth model that is petrophysically consistent and in agreement with all measurements, with the goal of better formation evaluation. This is our mantra. We're going to repeat this phrase in many ways throughout the class. And the way I like to visualize it is we're trying to build an Earth model that has a shield, which is to make sure that it's petrophysically consistent. That's what makes the Earth model relevant. And that is in connection with all the available data, meaning well logs, core data, experience from petrophysics or expert petrophysics people. And a way that I like that we like thinking about it is similar to the Sudoku. Most of you, I assume, have played this game. You are given a square with a set of numbers here in black, and you have to infer the missing numbers that are here in orange, following certain rules. You cannot repeat number in a row, you cannot repeat number in the column or in a box. We're doing the same thing. We have all the available data, logs, field experience, core data, and we're going to construct the Earth model following a set of rules, and those rules are making sure that all the measurements are honored and making sure that the entire model is petrophysically consistent. Meaning that if we say that there's that much shale, it's in agreement with the shale porosity, and it's in agreement with the water saturation, and so on. And the end goal is better formation evaluation again. The way everything we do with UTAPWeLS is modeling, and everything that we model is given a certain Earth model. Is constructing an Earth model. That's what we call our model. And it's a good idea to divide the concept in two. One, the geometry, another, the properties. The geometry, being technical, it's a skew cylindrical grid, which means that it's a cylindrical grid that it's skewed, which means the angles are not always 90 degrees, and it goes through along the well trajectory. And the angles are not always 90 degrees because we want to allow for trajectories that are not straight. Then we have layers that are crossing the well trajectory, and in between those, boundaries, and between those boundaries, we generate layers. I'm sorry, I'm going to mute everyone. Okay. Now, the radial zones are, well, beyond the well trajectory and the layers that we have around them, we're going to have the radial zones. So if we zoom into a certain area, we can imagine that it's a straight line, even though, as I said, it's not always a straight line. You're going to have the bed boundaries, and around them, you're going to have some radial zones, always symmetric, always just perfect circles around the trajectories. In every model, you're going to have at least one, which we call the borehole or the mud zone. So we always have that area. Then you may or may not have invaded zones, and it can be one or it can be multiple. And you will always have a formation zone, which is going to be after any invasion, you're going to have the formation zones. And that's going to fully describe the Earth model that we have. Now, in some simulations, there are some limitations that we cannot take into account the entire model. So we reduce that model into what we call a 1D or 2D or 1.5, 2.5. There's many types of reductions for these models. I'll admit more people in here. Now, the Earth model properties are going to be defined at any of these blocks. So any section that is between two bed boundaries and two radial boundaries, we're going to have a property. And that property is going to be piecewise constant, meaning it's just one value. And it's defined, there's 4 types of properties that we can have. They can be either full, which means they are defined for all zones, and they can change across all bed boundaries and radial boundaries. For example, resistivity. We can have another one, which is called petrophysical, which is not defined in the borehole and can change only across petrophysical boundaries, not radial boundaries. And later we're going to talk about the distinction between petrophysical boundaries and physical boundaries. In a few words, is whether they're fluid or not. And petrophysical properties are not fluid related. So petrophysical properties are only going to change when you are crossing a petrophysical boundary. For example, porosity. Then we have formation properties, which are very similar to petrophysical, but also but fluid related. So for example, neutron porosity. They're not defined in the borehole, but they're defined everywhere else. And they do change across fluid boundaries, including radial boundaries. And lastly, we have constant, which are defined for all zones, and they can change across all bed boundaries, but not radially. We only have temperature and pressure in this category. And now we're stressing this a little bit more because now you can have custom properties that the user can define at any moment. And we have one special property, which is called the rock class. Any layer, it's a petrophysical property, so it's by petrophysical layer. And what this property means is just a tag, just a name that we give to each of them, but that name associates that layer to a set of rock physics models. It can be and the models are resistivity, permeability, shale structure consistency. We're going to talk about these models a little bit more in the couple following talks. Then we have the effective medium theory for sonic, PCKR curves, permeability, NMR curves, physical inversion limits, compositional joint inversion. That's a set of models, and they keep changing and they keep being updated. Now, making sure we all have in mind, again, what is the main goal? We are going to use and honor all available data to build a petrophysically consistent Earth model for better formation evaluation. Now, with this in mind, I just want to say that we're not going to use UTAPWeLS, or UTAPWeLS is not meant to be your number one code program for petrophysics. If it's already well established, you don't need to. So some scenarios where you do need to use UTAPWeLS, or it's a good idea to do it, is cases where you need modeling like thin layers, like any system, well, thin layers including any system that has significant shoulder bed effects, any case where you have invasion, any case where you may have anisotropy, any case where you have deviated wells, where you have variations of logging tools of conditions, because if you work with Earth models rather than with logs directly, if the log was done different tools, if it's a lateral log or an induction tool, once you turn it into a physical property, the resistivity should be consistent regardless of what tool was used or what was the borehole conditions, what was the drilling mod. It shouldn't matter at that point. So you can combine what you learned from all these wells. Also, if you have complex lithology that is not fully understood, UTAPWeLS is going to help you test that. And just in general, uncommon petrophysics, meaning you have unique or novel rock physics models, UTAPWeLS is also going to help you understand what's going on. So giving you a quick overview of the software, when you open the main window, this is what you're going to see. And what you have installed here in the help menu, you have the application data folder. You can click there and it's going to show you this window. If you click open, it should show you something similar to this, which is where anytime you run a simulation, and we're going to talk about external simulations in a little bit later, all that data is going to go into this UTAPWeLS data. Any setting that you modify is going to go into this user preferences folder. That is information for your installation that is going to stay there. Think about when you in Word, when you decide to make default and showing the end of lines or not, and you close Word and it opens up again, and that stays there. The same thing happens here. And we have a number of things that we use that, including the plots that you use and so on. Then we also have the logs, which is anytime you use UTAPWeLS, it's going to show you the history and the licenses. And speaking of the logs, you can also here within help you have the log file, and if you click here, it's going to show you this location of where that log file is, and you can either open the folder or open the file. If you open the file, it's going to look something like this, which is just telling you the history of what you have done within UTAPWeLS, and that can be very helpful sometimes if UTAPWeLS crashes, which crashes really happen very rarely. But if something is not working, which is the nature of the beast, any piece of software is going to have these things, especially one that is being updated constantly and tested constantly. Whenever something like that happens, you will have an error here. You send us that file. It helps us understand what's wrong. We fix it. We give it back to you. This is our modus operandi. All right. Now, also in the menu here, we're going to have the project, where the project menu, where you have new projects, save project, what you would expect, save frequently because there is no autosave. We also have some project notes if you want to label whatever you have here, so that you remember what the project is about. And then most of the time, this is the main window, which you will use every time because it's the main window. And you will use this left part, which is the data tree. But really, well, most of the time you're going to be working with wells independently with each well. To add a well, you just click here and you're going to get this window, which is called the well interpreter. And this is really where you're going to be spending most of your time. You're going to be able to visualize data, load data, formation zones. You can specify them here. It's very easy to just give it a certain depth and it's going to show. And you can manipulate the Earth model, which is a set of modules that we have here, including the compositional palette, a module for boundaries. We're going to go into a little more detail on these modules in during the hands-on class, but just so that people know what we have, in case you don't stay for all of them. We also have a module to populate properties, so turning properties into Earth model, turning logs into Earth model properties. It would do something like this. The table view, which is exactly what it says, shows you the Earth model properties in a table fashion. The well geometry, where you can set up inclinations or logs or deviations and so on. The petrophysical calculator, Earth model, and at some point you will want to turn Earth model properties into logs, and for that we have this module that allows you to do exactly that. And you can have logs interact with Earth model properties directly using the general calculator, which we will use in a little bit, but you just define a number of inputs, define the output, and the output can be a Earth model property or a log, and you can perform any calculation. And now we allow user-defined Earth model properties, like I was saying before. Then going more into the UTAPWeLS specifics, we have the log simulators, where these are for physical properties. We have the resistivity, which we'll get into in the next couple of sessions. We have the nuclear simulator. We have the sonic simulator. These are the three most basic simulators that just take a property and take into account the formation properties and give you the tool response for that. Then we can do the opposite, which is turning, you have given a log, infer the Earth model property that is related to that. These are the physical properties inversion, which is what we usually call the MCMC. And then we have the compositional joint inversion, which is to infer the composition and all the petrophysical properties, including porosity, water saturation, shale concentration. So a foundation for hydrocarbon for volume. We also have a full session on this module. We also have the fluid flow simulator, which can perform invasion simulations and formation test simulations. This is one of the staples of UTAPWeLS. It's one of the most commonly used modules. There's a lot that goes into it. We also have a special session for it. And the end result is going to be just an invasion profile that's going to allow you to test how the tool response, the logs would look like at different invasion stages, and to really understand what's going on. We also have an NMR studio where you can calculate NMR response for a given Earth model. You can import data, you can make plots, 1D and 2D. You can perform inversion and analysis for going from decay to plot. You can also do simulations that include the shoulder bed effects. And you can lastly generate logs, which is something that most people are more familiar with, and turn this into more familiar logs to integrate into your formation evaluation. Something else that we do is, if you have been using UTAPWeLS, or if you paid a lot of attention into these slides, you saw that most modules in the bottom have three buttons, not just one, not just calculate, but they have one that says calculate multi-well and one that says IOO. That's short for interval of operation, which is modular to UTAPWeLS right now. And it's defining where the operation, being a simulation, being a calculation, being whatever operation that might be, where is that going to actually happen. By default, we're using the modeling interval, which for historical reasons is the main, not just historical reasons, it's what people are used to using. It's just defining an interval, top and bottom, and performing all calculations just in that zone of interest. That's why it makes sense. You can also do no constraint. You can do MD selections, which we're going to talk about in a little bit, which is exactly what it says. It's just selecting a set of measured depths, similar to modeling interval, but in this case, they don't necessarily need to be connected. And it's also good for visualization and for other things. We also have rock classes, so you can just say operate in this rock class. Also by formation zone, if you already know which one you're interested in, or specific layers. You can also set which wells you're going to run this operation. And that's when you would click the multi-well, calculate multi-well or run multi-well. That's the foundation for the multi-well framework. And you can notice here the other critical tool for really being able to do this multi-well is something we call mnemonic. If you click in this little button, it's going to open this window. Now going back here, what we have here in the output part is a source selection. So this source is going to give you the options of Earth model, LAS, or simulated or mnemonic. Mnemonic is just a generalization of logs, so that you don't need to specify a log set. You don't need to specify the curve name itself. You just say, I want the mnemonic that is this. In this case is DTSM, so it's the compressional. Shear velocity, travel time. And if you select this one, it's going to look in that well for all these curves. We have a very large data set of curves that was kindly shared by Wintershall Aldea. I think it works for most people, but you can modify it here. And if you or your company have a different set of mnemonics in an Excel page, or if you have other standards that you want us to implement, it's not too difficult. We can work with you. Anyway, what that's going to do is when you say, okay, I want to use mnemonic, and you choose any mnemonic, it's going to go over your well and find one of these curves and associate it to it. What this allows you to do is to, in different wells, you may have different curves. Now, all of them are going to behave the same way, and that's what you will do here. Not only that, but it's also, we've expanded the use of this so that you can also, for plotting, you keep some standards, you have some limits, you have the units that you're going to use for display, you have the scale, if it's linear or not, and the color of the line that you want to see, the style of that line. And then in many cases, you have that line might be a field log or it might be simulated. If it's simulated, you may have a different style. And lastly, you may have an Earth model property that is associated to this curve. So if you do, you would define it here, and you would define the style. And that wraps up the basics for UTAPWeLS.